Welcome to this RF Industry Icon podcast. I'm Pat Hindle, and I'm joined by my co-host, Eric Higham. In this episode, we're going to talk to Jim Cable, who is a pioneer in silicon on insulator CMOS technology, mainstreaming the technology at Peregrine Semiconductor, now pSemi, part of Murata. Welcome to the podcast, Jim.
Thank you. It's good to be here.
So you joined Peregrine in 1996, and you became CEO in 2002. And Jim led the company through the early design wins and rapid growth as it gained share in the mobile phone market, as silicon on sapphire technology displaced the pHEMT, which is the incumbent switch technology. Jim led the company to an IPO in 2012, and 2 years later coordinated the acquisition by Murata, which was their largest customer at the time. After the acquisition, Jim remained CEO and became CTO and chaired the board and served as a semiconductor R&D director for the parent company, Murata. But he retired, but not long. He's now chairman of the board of Finwave, which is another company trying to do a similar thing by mainstreaming GaN on silicon technology for high volume applications. So Jim, you studied physics for your bachelor's degree at University of California, Riverside, and then you went on to get a PhD in electrical engineering at UCLA. What led you into that area? Because I heard that you wanted to be a lawyer, which is a far cry from an engineer.
Yeah, so when I came out of high school, I kind of felt like I liked history. I felt like being a lawyer would be a good idea, but I was pretty good in math, and so I really didn't want to drop that path altogether. So I was undeclared, and I was taking liberal arts classes, and they were just really easy. So I took freshman physics, and the first midterm I got an F. And I remember I said to my mother, you know what? This subject's really hard. This is what I'm going to change my major to. So I also had a neighbor who was a good friend of mine who was a lawyer, and he told me, don't go into law. You'll be really bored. And so it was kind of a combination of those two things.
So you're always looking for a challenge, I think. I think that's kind of been your whole
Yeah,
career.
I mean, and the thing about the social science classes, it was just memorization, and you'd study for a test and you'd read all the material and then you'd regurgitate it. And, in physics, you get a crazy problem that you have to solve. It was just much more fulfilling, I guess I would say.
If we fast forward a few years, your first position was at TRW. How did
Right.
you pick them, and how'd you end up in CMOS versus gas?
That's also a long story. The primary reason I ended up at TRW was that TRW had an office in San Bernardino. I went to school at UC Riverside. I grew up in Redlands, so they were all very close. And I learned of a position there for like a summer job. So I went to work in the summers at TRW. It was not in electronics, really. It was in some other areas. But when I finished my bachelor's degree, it was pretty funny that my boss said to me, he said, well, we can't pay you as an intern anymore because you're now an MTS. And I got a 55% raise just by getting my degree. And then I decided I wanted to go to grad school and do double E. And so TRW had some programs that would support you at either USC or UCLA. And so I went to both schools. I liked UCLA a lot better, primarily because of the location. And TRW transferred me to the Redondo Beach site. And that's where both the CMOS fab and the gas fab were. I don't know. At the time I thought gas was kind of black magic, and so I went the way of the CMOS group and did various positions there, and that was kind of my experience at TRW. I would say that if you look around the industry, there's an awful lot of people that came from TRW in microelectronics, either in gas or CMOS, and it was really a great place to be innovative and creative, and they didn't hold you back just because you were young. It was a great experience.
Yeah, they have some great technology there. They've always have.
Yeah.
So did you do both? Were you working at the
No, I
same?
never did gas. I have a lot of friends that did gas, and we still keep in touch. And it was always kind of a little bit of a rivalry, who would get more R&D money. And, eventually TRW decided they couldn't have state-of-the-art facilities in both. And, for their core business was spook satellites. And so gas made a lot more sense. And so I understood the reason why TRW closed the CMOS fab. So I have no hard feelings.
Can you expand on that just a little bit? Some of the thought that went behind TRW deciding to shut down that CMOS process, and is that why you went to Hughes, or was that more to do
Well,
with
they
location?
decided to shut it down, I think, because, at the time we had done the VISIC 2 program, which was half micron CMOS, which was a huge leap forward. And we were partnered with Motorola. And we actually were getting higher yields out of our process than Motorola was. But, the fab was 4-inch. And by that time, sub 1 micron technologies were starting to be available at commercial guys. And, if you look at the cost to upgrade 4-inch to 6-inch and then eventually go to 8-inch, it didn't make sense for TRW to do that. And so when they announced that they were closing down, I pretty much made up my mind that I would go elsewhere. I stayed at the company for another year, I think, just doing some program management stuff, but that was boring. So I went out to look for another job in microelectronics. By that time, I was, thoroughly hooked on that field. And I interviewed at companies really across the country. And frankly, I could have gone pretty much anywhere, but for quality of life, I decided to. I'd always been kind of a big ocean water person, and I always wanted to get down to San Diego because the surf was better there. And so Hughes came along and offered me a job in Carlsbad, which was fantastic. And so, yeah, that's really why I went to Hughes. I didn't really think that long term it would be so viable, but I was young and single and seemed like a good next step.
Yeah, can't blame you for that decision.
Yeah, so yeah, that's the truth.
And so it seems like Hughes also decided to shut down their CMOS efforts. So how did you end up at Peregrine?
Well, that's also an interesting story because I went to Hughes Carlsbad, and they were the part of Hughes that was doing silicon on sapphire. And they actually decided to close that facility down and move that silicon on sapphire because they were using it for, satellite programs. And it was pretty important to the company. So they wanted to maintain that capability. And so they moved it to Newport Beach. I was in charge of that move. And eventually at the Newport Beach fab, I became operations and technology manager. And so the reason it's interesting because when Peregrine first started, Ron Reedy, who I'd never met, called me when I was at TRW because I was kind of running the CMOS R&D activity. And he came up and we talked, and he said they were doing this fully depleted silicon on sapphire. And we had done a lot of work in early SOI, and it was pretty challenging. This was back when people were doing SIMOX and other things like that. And so, anyway, I talked to one of the guys who worked for me who had done silicon on sapphire in Russia, actually, before he came to this country. And so I told him about what Ron had proposed, and I asked him, I said, do you think we can run silicon on sapphire in the fab? He goes, yeah, it'll be no problem. So we actually built the first wafers for Peregrine at the fab we had in El Segundo. And, we actually had signed some agreements that we would, be a low volume foundry for them. And then they closed it down. And then since I went to Hughes and they were doing really big silicon on sapphire chips for the space applications, we were getting great yields. And, people said, silicon on sapphire won't yield. But in fact, we were getting quite good yields. And so when Ron called me again, this was like 96, he said, hey, I know you guys are doing a lot of SOS Newport Beach. Why don't you come to Peregrine? And, I could see the writing on the wall at Hughes. So I said, yeah, what the heck? Now I'm really in San Diego. So I made it to, first San Diego at Carlsbad, then Orange County at Hughes, Newport Beach, finally Peregrine in San Diego. So, I was running a pretty big organization. It was probably over, I don't know, 100 people. And the thought of joining a raw startup was kind of scary,
Right.
but
Right.
anyway, I did it. And it was a kind of the time when pioneering professors were doing RF CMOS. A lot of that was Berkeley and UCLA, and I knew some of the professors. And so I thought, this would be a great way to do RF CMOS. And so I joined Peregrine.
Yeah, interesting. So you've done a lot of CMOS activities and
Yeah.
at companies that have closed those activities down.
Yeah, exactly.
Do you think it was just bad timing? The infrastructure wasn't in place. Why do you think those
Uh,
companies abandoned in favor of gas?
Again, I think that both of those companies had subscale silicon capabilities. And so again, at both Carlsbad and Newport Beach, they were 4-inch fabs. It was really hard to compete commercially. And the cost of upgrading, again, those fabs were there primarily to service the internal customer. And, we kind of used excess capacity to do what commercial work we could find. We did ship a lot of product to Delco. So we did a lot of commercial production in Newport Beach, but it was hard. It was really hard. So again, I could see the writing on the wall, and I said, "Look, I'm going to make the jump." I'm sure that Hughes is still doing gas, certainly HRL, and so again for at the time for what Hughes was doing, yeah, gas made more sense than silicon. You could do it on smaller wafers and so again, I kind of accepted that. And again, I guess I kind of looked at it. I really wasn't that worried about getting a job. So, if I went to a place and it closed down, I kind of figured I'd land on my feet. So, don't sweat it. And, quality of life was important to me. So, getting to San Diego where Peregrine was kind of, a fantastic opportunity.
So tell us how you led to believe that RF CMOS could become a competitor to the gas PM technology. How are you so strongly believing in that? What were some of the things that you looked into that convinced you that that was the way?
Well, early on, we had done some switches, and these were kind of lowish power switches. And again, the Sapphire was a perfect insulator. So from the standpoint of generating linear switches, it was kind of an ideal solution. The gas switches at the time are PHEMT, and so they needed negative voltage, which certainly a lot of people didn't like. Certainly in handsets, they didn't like it at all. You needed blocking capacitors, you needed independent drivers. And, the advantage of CMOS is you can integrate all of that stuff. You didn't need blocking capacitors. And we needed negative voltage to keep the SOI switches off. So we just built a charge pump and took the battery voltage and pumped it to the -3 volts, and we could hold the switches off. And so we won some early, switch sockets, I would say sub 1 watt. Um, and the feeling was amongst a lot of the people on my team that you could not extend that at the time. Of course, everything was GSM. GSM power levels are quite high. And so most of my team felt like there's no way we can do that because our breakdown voltages are so low. I mean, this was like 3-volt CMOS. And so, but we kind of worked through all this and we found that by scaling the gate length a little bit more, we could do as many as a stack of 9 transistors and it still had pretty good insertion loss. And so we started winning GSM sockets using that technology. And then when 3G came around, all of a sudden linearity got to be important. And, we had linearity that I would say was a little bit better than gas. But then we invented something we call HARP, which just blew the doors off everybody in terms of linearity. And with one single HARP was a design change. You know, one simple design change, we improved our linearity by 20 dB. So Eric, you know what that means. That's like breakthrough stuff. So I want to say in 2011, those switches were designed into the top 10 handsets in the world. And those were still all on silicon on sapphire. But what was happening by then was sapphire, you could only get up to 6-inch wafer sizes, and it was expensive. Today, 6-inch sapphire is very cheap because of the LED market. But there was no real path to 8-inch. And we were kind of doing quarter micron-ish lithography on 6-inch wafers, but there was no roadmap going forward. And so the last generation of sapphire that we did, we worked with Soitec, and that's how I got acquainted with Soitec. And we did something we call bonded SOS. So we took a SOI wafer and bonded it to sapphire because at the time SOI didn't have very good RF properties. And so that BSOS won every socket everywhere, but it was a little expensive. And so Soitec, we worked with Soitec on this trap rich, high resistivity. We were the first guys to use it. And it worked really well. So all of a sudden, 8-inch became possible, and then we could really go to town. So unfortunately, I would say a lot of people, let's just say, borrowed that HARP IP, and Murata was not big on patent assertion. So they kind of told me, just let it go. So we kind of gave everybody a free license to some very, very valuable patents.
Interesting
Which
business
didn't
decision.
make me happy, by the way.
We couldn't tell.
Yeah, yeah.
And, you know, I would say we then, after we had invented this sort of stacking idea for switches, we said, well, why don't we apply something like that to PAs?
Mhm.
Where again, the issue was how do you handle the higher voltages? And again, we came up with an alternative way of doing stacking for power amps. And we built some GSM and LTE power amps that were pretty amazing, but that was right about the time Murata bought us, and they had their own internal PA team. And, you know, we tried to work with them, but, you know, they didn't want us eating from their rice bowl. So they made it really, really difficult. But we came up with a method to do that kind of stacking for PAs that is, again, very, very widely used in the industry today with SOI.
So I think you've probably have touched on some of what I'm about to ask next, but you've kind of been around since the birth of RF CMOS technology.
Yeah, yeah.
And what were the main challenges that you've seen, and how did you overcome them?
Well, you know, the challenge for any new technology company is you're competing with an incumbent who has a long trail of shipping product and quality and all that. So you have to give potential customers a real advantage, or they won't really even look at you too far. So we had to do a lot of education. It was pioneering selling. We took a lot of arrows like most pioneers do. And a lot of people thought, what you're saying, it's not possible. I remember what kind of led to us believing that we were right is we took some GSM switches into Nokia, and they said they would test them for us. And so a couple of weeks later, they contacted us. They said, wow, they said, they don't exactly meet our spec, but they're really close. And they said, we don't buy, switches directly. We buy them through module partners. And they said, our biggest module partner is Murata. And so I had tried to get in touch with Murata before Nokia. And they basically, it was hard to get a return call. So at the time, Suneo Murata was the president of Murata, and he was good buddies with the Nokia purchasing guys. So they called Suneo, and all of a sudden, we were able to get a meeting with Murata, and they became very interested in our products, and they funded some NRE, and then the relationship just grew from there. I would say the second biggest problem we had was supply chain. Most fabs don't particularly like the idea of running sapphire in their fab. There's some challenges. It's transparent, which means the fab sensors have some challenges sometimes. You have to kind of reset them. The weight's a little bit different. And sapphire is aluminum oxide. So people were afraid that, that aluminum would out diffuse from the oxide. And aluminum, of course, is a dopant in silicon. And so we had to go through a lot of those kind of studies. But it turns out it's actually the aluminum and the oxide are very tightly bound, and you have to, go to extreme temperatures for them to disassociate. But we had the CEO prior to me had concluded that we needed to own a fab because we'd been working with foundry folks in Japan, and they both closed. So I have a lot of history with fab closings.
You
And
sound like a
so
master at it.
he said, we need to buy a fab. And I was like, oh man, you've never run a fab. You don't know, it eats money, blah, 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 blah. And he goes, let's find a fab, Jim. I was COO at the time. And I was like, okay. So anyway, we found this fab in Sydney, Australia. And we basically installed our silicon on sapphire technology there. And that was really all of a sudden we could get it qualified. We could ship lowish volume products. We had all the reliability data. And in the meantime, I had been working with Oki in Japan to do a dual source. And about the time that our handset volumes really took off, we just couldn't keep up in the Australian fab. There was too much demand. And by that time, Oki was up and running and qualified, and we basically had to sell customers that were using the Sydney fab that they had no choice. If they wanted the product, they had to use wafers from Oki, which was it was a stressful time, but at the end of the day, Oki could produce whatever volume we wanted, and they, because it was a much better fab, they got better quality, and so the relationship we had with Oki was actually, I would say, saved the company because the handset guys were ordering so much that, by the time I used to get to my desk, there'd be four like messages on my phone of really pissed off customers. So, it was great when that ended. So I think those were the two biggest things. New technology is always, competing against an incumbent, which is known. And secondly, the sapphire supply chain we developed the whole thing. I mean, we were the first guys to do 6-inch sapphire. We were the first guys to figure out that you could laser cut sapphire as opposed to sawing it. So, we pioneered just about everything in silicon on sapphire. But once the RF SOI really showed great substrate behavior, there was no reason to stick with sapphire.
Very interesting. So let's turn a little bit to the business side. How did you lead Peregrine to IPO and then later the acquisition by Murata?
Well, the IPO was the natural exit for us. I think when we did the IPO, we had 200 million in revenue. We had tier one customers. And it was an era where semi IPOs could happen. The window was open. I had tired investors that wanted an exit. And it had taken a lot of venture capital to get us to that point. So the IPO was the only approach that made sense. And so that was quite an adventure. A roadshow is something I wouldn't wish on my worst enemy. Being a public company CEO is not a walk in the park either. And the reason by that time, Murata was a huge customer of ours. And we got an inbound M&A offer from somebody who was a competitor to Murata. And then we got a second one. And, so you're a public company, right? The board goes into action, they hire bankers, they start shopping it around. And I had, when they did the NRE with us way back, I had told the CEO of Murata and his right-hand man in the module business, that's Norio Nakajima. And he was really the guy who was our customer. He's now the president of Murata. And so I called him and I said, hey, I promised Murata that if any potential competitors were trying to buy us, I would let you know. And I said, we actually have two. So I'm not trying to put pressure. I'm just, I promised this. I'm following through on my promise. And he says to me, okay. He goes, I need to check with, the CEO and the CFO, and I'll call you back tomorrow. I was like, okay. And so he calls me back the next day and he goes, okay, we're going to buy you. It was like not a huge committee event. And so, that went through. I would say it worked well. We became their, by that time, semiconductors were an important part of the front end modules. They didn't have any internal semiconductor capabilities. So it was kind of a match made in heaven. We sold die to them. They put our die in their modules and they sold it into, tier one handset guys. So we sold billions of parts to guys like Samsung and Apple, but it was never a Peregrine branded part. It was always a Murata module that had our die inside. So, and that's still kind of the model that pSemi follows today to a very large degree.
So if we talk about your latest adventure, how'd you get involved with Finwave and what are you doing with GaN on silicon technology?
Yeah, so in my last years at working for Murata, they asked me to be the director of worldwide semi R&D or some title like that. I don't remember exactly what. And so we had funded an NRE project with Finwave. At the time, it was called Cambridge Electronics. And that NRE was to do, I had recently just purchased this company, Arctic Sand, from Murata that was doing power management using switch capacitor techniques. And they were very interested in looking at GaN for those power management chips. So we had funded an NRE. So I knew Ben Liu, the founder, well from those days. And when I quote retired, that lasted about a month. And I don't know, it was probably 4 or 5 months later that the Cambridge Electronics board asked me to be on the board. And I said, no. And they were like, well, why? And I said, because I don't think the company will be successful in power GaN. I said, there's old established guys, there's new startups, you got Navitas, you got EPC, you got GaN systems. And I said, and more they're going to go to modules, which need pulse width modulators and passives and all that stuff. I said, it's a complicated supply chain. But in that kind of period of time, I had looked at the papers that Cambridge Electronics had published. I looked at Ben Liu's thesis and read it, and I became convinced that there was a compelling opportunity for GaN on silicon and RF. So I told the board, I said, look, if you pivot the company to RF, I'll consider joining the board. So I had to tell them why, blah, 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 blah. And they called me sometime later and said, okay, you convinced us. We'll pivot the company. We want you to be chairman. I was like, oh, be careful.
You got a
what
promotion
you
over that.
So anyway, I was chairman of the board for, I would say, a couple of years, but I was executive chairman because I was also kind of responsible for strategy and, I was introducing the company to, other potential customers. I have a pretty good network from my pSemi days. And after I joined, the kind of the first thing they told me is, well, we're going to run out of cash. It's like, great. So we quickly went out and raised a bridge round. And I would say that was largely through folks that invested in Peregrine in the early days. So friendly investors. And I brought in Soitec because, there was a lot of history there. And then we did a Series A. And again, that was very successful. And so when we did the Series A, the board gets reconstituted, right, with VCs that led the Series A. Well, it was at sometime last year we brought in a new CEO, And so the CEO had to get a board seat. So I'm no longer chairman, but my title is Chief Strategy Officer, and it's really a full-time job now. So the reason I came to believe that GaN on silicon made sense for RF in spite of previous failures is that the previous failures were trying to do very high power RF. And they were also doing it at a time when epi growth on silicon was not nearly as good as it is now. And the problem with high power RF is thermal. And of course, thermal affects reliability. But if you look at what's happening now with, say, small cells and these big phased array systems, the power per element is dropping to very small levels. And so, if you do a 5-watt PA or maybe 10-watt PA, the silicon, GaN on silicon can handle that very well. So it's not an issue. And, if you go up in frequency, the power levels per element come down even more because you have more beamforming. So, and the linearity you can achieve with, our fin devices was pretty spectacular. So that's why I felt there was a huge opportunity in RF. And because we were running it even in the early days on 8-inch wafers, it was pretty easy to see how, it was really scalable. I mean, a good 8-inch fab can print 90 nanometer gates, probably push it to 65. And again, we had set up the process, this was before my time, to be completely CMOS foundry compatible. And so, again, that was why I believed in silicon on sapphire versus gas. You could run it in a silicon fab. And here we had a way to run 8-inch in a silicon fab and, potentially scale to 12-inch. And so I was like, if you want to look at high power, high frequency, and high power meaning, let's just say less than 10 watts, you can't beat GaN on silicon. And of course, more and more markets are going that way. I mean, you've got FR2, which is millimeter wave, and then you have people talking about FR3, which is 7 to 20. And then you got satellite guys that are doing Q and V band. And it's really hard to generate a lot of power at those frequencies. And it's not that big a problem for us, given that we can do the gate length scaling that I was mentioning.
And so where are you standing right now with Finwave? What's their status?
Well, so we're in a kind of an interesting position right now. So we actually are sampling some high power switch products that are, I would say, not really aggressive lithography because the fab itself isn't capable of that. But, we're doing like 10, 40-watt switches. And there's a lot of customer interest in those. So we're sampling those today. And we're in the process of consummating a deal where we would transfer the 8-inch technology, which we're currently running at a prototype fab, into a major high volume foundry. And I can't talk too much about the specifics there, but I think you'll see a very interesting announcement sometime in May that discloses that, certainly before IMS.
So, Jimmy, if you started to head down this path a little, and I'm sure you knew it was coming, it's the crystal ball question. So what do you see as the biggest semiconductor development in the next 5 years?
Well, I mean, certainly, there's going to be continued scaling, which, people said, when I was in grad school, the theoretical limit of scaling CMOS was 130 nanometers. Well, guess what? That was wrong. I think advanced packaging is going to become more and more important because it doesn't make sense to really, have all of your SOC on a 3 nanometer node, when, that's an expensive node to operate at. So I think, standard chiplet architectures will become more and more common. I think on the RF side, I think most people are going to start realizing that going forward, GaN on silicon is a great solution. And I, people, when I talk to them, they say, God, Jim, you were like a pioneer in RF SOI. You've changed your tune. And I say, no, I haven't. I think the two complement each other really well. The downside of GaN, if you will, is you can't do logic. I mean, it has an N-channel device. And so you can't really do sophisticated beamforming or anything like that on a GaN die. But you can use a CMOS die as a companion and do all the control, and in a PA, the biasing and all that sort of stuff. And, for packaging houses to put two die in a package is no big deal anymore. So I think more and more will kind of go that in the future, go that hybrid route. Because again, people are doing very high frequency PAs and CMOS, even at 28 gigahertz, but they're low power. I mean, you can get maybe 15 dBm of linear power, and you can get away with that, in a base station application that has 10,024 elements. So you make up with the lack of power with, massive amounts of antenna gain. But, in a handset, the form factor is such that, and if you look at 5G today, certainly on the millimeter wave side of 5G, it's massively uplink limited, like 15 dB. So the link margin downstream is quite good. The link margin upstream is not very good. And so there's real interest in higher power PAs for that application. Same thing is true with CPE. You got this huge base station out there that's sending the signal for, FWA, and the CPE, you can't, nobody wants a huge antenna on the side of their house. So you'd like to have higher power. So I think, if you look at probably the most aggressive GaN on silicon for RF that's been done was done by Intel. It was 30 nanometer. It had like 400 or 500 gigahertz FT and Fmax. I mean, that's kind of shows the potential.
Yeah.
Much higher breakdown voltage with GaN than you do in silicon because of the electric field issue and the wider band gap. So it's really pretty remarkable technology from an RF perspective. It just doesn't have the same integration capability that we had with RF SOI.
Has much better efficiency too. Do you see GaN going into the handset? Because it's very high voltage, so.
Well, no, that's what most people think. And I would say that's where most of the GaN activity has been. If you look at the GaN that's in infrastructure today for, say, macro base stations, it's depletion mode GaN, and it's very high voltage, say 48 volts. The GaN that we're doing is enhancement mode GaN, which no handset guy wants to use depletion mode. It's enhancement mode, and we can run it off 5 volts, 3 volts. So you can run it off a handset, there's no doubt. I would say, and we have a lot of data that shows how good it is in that kind of handset application. The challenge for getting GaN on silicon into handsets is the supply chain. I mean, there's no foundry in the world that can manufacture enough of that to get a handset guy to say, I'm ready to convert over. And that supply chain is limited both in terms of the foundry as well as the GaN epi. So until the supply chain gets much bigger, GaN on handset is, yeah, you can do it. We can demonstrate it, but it needs more backing. It needs an ecosystem today. There's no doubt that technically it's very doable and has some real advantages.
Well, excellent, Jim. Thanks for sharing your experiences and insights in the industry. Really appreciate it. You've inspired many revolutionary products, and you're still at it with Finwave. So we hope to see how that goes.
I can't seem to give it up for some reason.
Yeah, you'll retire again for a couple of days, and somebody will find you.
Yeah, I don't know. I'm pretty old now, so I think this might be my last real gig. I don't know. I always say that, but I get asked by a lot of people to be on boards and consult, and I'm starting to say no, enough's enough.
There you go. Well, you're truly an RF industry icon, so we appreciate you doing this podcast. To our listeners, you can find more podcasts at podcast.microwavejournal.com. Thanks for listening.